Okay, so thank you everyone, and welcome to the seminar series. I'm not Chris Malcolm, obviously. I'm just stepping in at the last minute. It's really my pleasure to be introducing today one of the newest faculty members in the Department of Chemistry, Dr. Shrinwantu Pal. So Dr. Pal did his undergrad honors in chemistry from the University of Calcutta, also did a master's degree in India, and then did his PhD at the University of Maryland, College Park in the US, followed by postdoc fellowships at UBC and University of Tokyo, and I think was most recently a research assistant, one would say, at University of Calgary. Now, and he's also quite accomplished with quite a number of publications. I think that today's talk is more about a little stint that he did in industry. And so this talk today, I think, is about work that he did on developing carbon negative cement or concrete for a company called Carbicrete in one of the suburbs of Montreal. Because I think we oftentimes forget that making cement comes with a lot of CO2 production. So tell us all about it.
Okay, thanks, Mike. It's a great pleasure to be here and talking about some of the industry stuff that I did in Montreal, essentially, for people that don't know what Lachine is. I do love that place. It's a nice little, as Mike said, suburb next to the big river called Bord du Lac. Anyway, really the reason I chose this topic as opposed to the stuff I do in my chemistry lab is that I have been told by numerous faculties, mostly at UBC, that when I present chemistry stuff, they feel like they were hit by a bus. So in other words, I wanted to come with a topic that is more appreciated by the general audience, in other words, non-chemistry audience. There will be some chemistry here, but mostly it's related to making cement and concrete and how to do that in a carbon negative fashion. So we don't need a big introduction about what climate change is. We know that this is an imminent threat to how the planet is coping with huge amounts of CO2 being dumped into the atmosphere. These images just show that, one of the biggest contributors is industry, where you have tons of CO2 being dumped by factories into the atmosphere. We are aware, for those who have recently traveled to BC, specifically Kelowna, we know what's going on there with the wildfires, which have been shown that they're related to climate change. And we also know that what's happening around the equator, that the temperature is actually increasing, making obviously the polar ice caps melt slowly and increasing amount of water in the oceans. The critical element that is responsible for climate change is obviously CO2. That needs no introduction. The increasing CO2 manifests in rising temperatures. What I would like to point out here specifically is that this scale is in thousands of years, but if you look at the last little bit, and that's not even 1,000 years, that's a fraction of 1,000 years, but you can clearly see where we are and how, based on the thousands of years before, how we can, the slope of this curve is just almost infinity. This rising temperature also manifests in rising sea levels. And as you can see, it's constantly increasing. NASA projects that every year we're getting about 3.6 millimeters of increments recently. Tides are a little less susceptible to the overall increase because tides are a way of nature's way of kind of equilibrating the rising levels. But still, even in tides, you see a big increase in terms of how the tide levels are increasing. Before we begin to address how to remediate the problem of CO2, we must understand where CO2 comes from and what the processes are that contribute to CO2. We all know that industry, combustion, we driving our cars are all dumping CO2 into the atmosphere. So specifically, combustion is primarily the biggest contributor for CO2. Biological, as you're living, you're breathing oxygen, you're burning carbohydrates, and you're generating CO2. So there's a big biological component. Sorry, there's a lag here. I'll get used to it. There's a big biological contribution to the amount of CO2 dumped into the atmosphere. Little less known, perhaps, is the effect of the atmospheric CO2. We'll come to that in a second. But what atmospheric CO2 is essentially the CO2 that is already present in the atmosphere gets equilibrated between the air, the water in the oceans, as well as the ground. And it depends on a fine equilibrium. So that's also a contribution for the CO2 in the atmosphere. What is less known, and Dr. Malcolm was telling me last week, what is less known is the amount of CO2 that cement produces on a global scale. It is by far the biggest contributor towards CO2 in the atmosphere. We take cement for granted. We're sitting in a room made of cement, made of concrete. And as we approach our efforts to mitigate or reach carbon zero, we must admit that cement, which is in everyday lives, is a big contributor to CO2 in the total amount of CO2. CO2, on the other hand, can be used. So in the title, IO is just a fancy way of saying input output. People who work in technology or IT sector would completely understand what IO means. It's input output. So on the left-hand side, it's output, and on the right-hand side is input. So CO2 can be used in many fashions, but some of them are reversible and some of them are irreversible. So as I show here, we'll come to the mineralization in a second, but CO2 is used by plants in photosynthesis to make food, carbohydrates, essentially. CO2 is used in the chemical industry to form a variety of compounds, most notably polymers. CO2 is used in fire retardants. I don't know if we have a red tank here, but if you walk around the chemistry department, you will see some fire extinguishers that are CO2 based. CO2 is more recently used as refrigerants because we all know that traditional refrigerants like halocarbons are bad for the ozone layer. So there's been a big movement towards using CO2 as a refrigerant gas. CO2 is also recently found use as a hydrogen storage medium. Coincidentally, this is also my primary research focus on how to use CO2 and CO2-like molecules in hydrogen storage. Hydrogen is the new frontier of energy. So this scheme overall shows that how CO2 is used and formed in the environment. Since cement produces a lot of CO2, and CO2 is consumed as mineralization, and what I mean by mineralization is the permanent fixation of CO2 as carbonates, one can wonder if these can be coupled. In other words, we're already seeing that in the environment, CO2 is used to form minerals. On the other hand, cement, which is kind of a mineral that generates CO2, the obvious question is whether cement and mineralization can be coupled together. But before that, let me just talk about what mineralization exactly is. So we start with CO2, which is, let's assume, completely in the air. As CO2 undergoes hydration, to a chemist, hydration is probably not the best word, but to non-chemists, hydration just means the reaction of something with water. In chemical terms, CO2 reacts with water to form carbonic acid. I had hoped there would be a soda bottle today that I would open right at this moment and show that this reaction of CO2 to water is actually reversible. And what I hope to do is open the soda bottle. This is not me saying that, get soda next time, but what I mean to say is that if you note the arrow, the bottom arrow is smaller and the arrow pointing towards the bottom is smaller and the one pointing up is bigger. In terms of equilibrium, essentially what it means is that the carbonic acid that is generated by reaction of CO2 and water would preferably lie on the CO2 side, and the carbonic acid side is actually less stable. This, of course, can be balanced by pH. In other words, if you take as I mentioned, the word is carbonic acid, which means it's an acid. Therefore, if you could somehow take away the protons, then you could actually convert carbonic acid to something called bicarbonate. If you take off another proton, you generate what is called a carbonate. So in both of these steps, if you can control the pH, essentially by keeping it alkaline, which means you're taking away the protons, you can actually shift this equilibrium, which was unhappy to come to the carbonic acid side, you irreversibly move it over to the carbonate side. This is exactly what has been happening for thousands of years in nature, where in water, there's a mineral called olivine, which is a magnesium silicate. It's called olivine because it has a characteristic green, almost like those chairs over there, color. It's beautiful to look at. I'm sorry, I don't have a picture, but olivine is alkaline, and in seawater, olivine reacts with one of those protons to form silicates and silicic acid, which gets trapped in the Earth's crust here. Now, as this reaction proceeds, you can take up another proton, indirectly in this case, where the calcium ions in seawater trap the carbonate to form calcium carbonate, which is limestone. Now, for those of you who attended the talk last week by Aaron, and I mentioned that Aaron was basically digging up, and correct me if I'm wrong, limestone, shale limestone, things like that, and he was dissolving those substrates in HCl to unearth the fossils. Essentially, what he was doing was he was reacting the calcium carbonate with HCl, and that carbonate was being released as CO2. What I want to point out here, though, is that in nature, as long as we keep the pH of the seawater sort of alkaline, this process of going from CO2 all the way to limestone is a form of permanent sequestration. So if we could somehow have a lot of base and dump it into the seawater, sure, we'd kill all the creatures in the sea, but Aaron would be there, a million years later to get their fossils. But nonetheless, you could convert all the CO2 to calcium carbonate and reduce the CO2 levels. Unfortunately, that's not a practical solution. That being said, this reaction of converting CO2 with calcium ions in an alkaline phase is a big deal because it not only is permanent, but it also generates a lot of energy. This reaction overall is an exergonic or exothermic, sorry, I correct myself, exothermic reaction, releasing between, depending on the mineral formed, 15 to 45 kilocalorie per mole of calcium carbonate formed. For those of you who don't know or don't have a feeling of how much this energy is, when you boil water, each mole of water going from the water phase to the vapor phase takes up around 30 kilocalorie per mole. So that's kind of a big deal. When you think about how much energy, how much heat you need to boil water, this is kind of a big deal. So now that we know that we can permanently sequester CO2 with calcium in alkaline conditions, let's look at how cement contributes to the formation of CO2. So traditionally, cement is made by a process called calcination. In this process of calcination, what is done is essentially calcium carbonate, so Aaron's stuff here, is taken, mixed with sand. In this reaction, sand is just acting as a dispersant. The reason I say it's only acting as a dispersant is because this is not technically a chemical equation, because SiO2, sand, stays SiO2. So at this point, sand does not have a chemical role, it's just a dispersant. So calcination essentially is just calcium carbonate being heated, releasing CO2. If you balance the reaction, you'll see that once you take out CO2, you end up with calcium oxide. Then calcium oxide comes in contact with the already dispersed silica in the medium and forms two important compounds. When I started working at Carbicrete as a chemist, I had no expertise in cement, and I was surrounded by a bunch of engineers, and they kept telling me C2S and C3S. To a chemist, C2S means 2 carbons and 1 sulfur, or C3S means 3 carbons and 1 sulfur. And I was amazed that these are compounds, but no, these are not compounds. They're just notations used by the concrete industry. The reason C2S and C3S is named as such is because if you look at the top compound here, sometimes it's a pointer, interesting. So this calcium oxide has 2 molecules of calcium oxide combined with a molecule of silicate. So C2S here just stands for dicalcium silicate. And the one that has 3 calcium oxides is tricalcium silicate. This, in a sense, forms the chemical composition of cement. So now that we know the chemical concept of cement, how does cement get fortified? How do we mix cement with water and we are able to build buildings that hopefully don't fall apart? The reason cement undergoes the way how cement undergoes fortification is basically a reaction called hydration. So you take cement, which is also called mortar, and you mix it with aggregates, which are usually pieces of stone and gravel, and you combine them with water, and you let them set. In concrete industry, this block that you've made with molds is typically called precast concrete blocks. As the cement undergoes the hydration reaction, you're basically generating a new mineral that is calcium silicate hydrate, which is called CSH in the concrete industry. This is a 3D network of calcium silicate and water formed, and that embeds all the aggregates inside to form your precast concrete block. So in a sense, you should realize that cement and concrete are not the same thing. Cement is just a binder which undergoes hydration reactions together with aggregates to form this 3D structured block, depending on your size of your mold, and you get your concrete block. The primary reaction responsible for the strengthening of concrete is a hydration reaction. There are smaller reactions that contribute to secondary strength of cement, which I won't actually go into, but there's aluminum involved and also sometimes iron oxide to form other minerals. But you have to appreciate that this calcium aluminate is very similar to the calcium silicate written here. So the primary strength is the CSH formation, while the secondary strength comes from minor reaction. As cement ages in the atmosphere, cement actually sequesters some of the CO2 and converts some of the calcium hydroxide and calcium silicates to calcium carbonate and releases some amount of water. So the question is, if cement already does this and the formation of cement generates a lot of CO2, oh well. Yeah, somehow. Okay, there we go. And the production of cement generates CO2. The question therefore is, can we just couple those two things together, and then left-hand side CO2 and right-hand side CO2 would just cancel each other out, and therefore you could reach potentially a carbon negative solution. So I'm going to change gears here, and I'm going to tell you a little bit about iron extraction. And I'm sure in your mind, you're like, he was just talking about cement, and now he comes to iron extraction. The reason will be apparent later, but for now, just ride with me and see what iron extraction is all about. So how do we do iron extraction? Is basically a very simple reaction in which we take iron ore, which is Fe2O3 or Fe3O4. We mix it with coke, which is not cocaine, it's carbon, which is industrial term for carbon is coke, it's coal essentially. We mix it with sand and calcium carbonate, and we heat it in a blast furnace where oxygen is being pumped through the furnace. In the blast furnace, the reaction that happens is essentially the coke reduces the iron to form iron metal. Come on. Okay, which we've all seen these images of people extracting the liquid molten metal. If you've watched Terminator, you've seen what molten metal is like and how it can kill Terminators. But essentially, the molten metal comes out of the bottom because the density of iron is heavier than the density of all other products formed. What happens to the silica and the calcium oxide is it forms calcium silicate. And if you recall, calcium silicate was a component of cement together with the formation of calcium oxide. This, and pardon my French here, crap is essentially thrown out of the blast furnace and nobody uses it typically. It is dumped outside. People have tried different things, but it's usually dumped outside the factories or taken to landfills where it solidifies and forms this not pretty gunk of mud-like looking things. But it has a lot of potential because it has a lot of unreacted calcium oxide, which, as we've studied before, is basic in water. So if you could somehow take the calcium from the slag, that was the garbage material, and you can react it with CO2, you could potentially form calcium carbonate. As a spin-off of McGill University, one of the founders of the company I worked at in Montreal discovered that you can essentially take the blast furnace slag, you can grind it up, and you can expose it to CO2 in the presence of water, and that would actually fortify. I won't go too much into the reactions here, but the top reaction is essentially very similar to the hydration reaction that happens in cement. From a physical perspective, this is what happens. So you have the particles of slag that have been now ground together with aggregate. This is a very bad rendition, but this is how it's supposed to look like. You have something called a pore, which is essentially a hollow space between the slag particles and the aggregate particles. Within this boundary between every slag particle and pore, you have a very thin film of water through which the calcium, unreacted calcium, percolates and comes out into the pore or the aqueous solution surrounding the slag particles. In that aqueous environment, the calcium undergoes reaction with CO2 in the presence of water to form calcium carbonate. We all know that calcium carbonate is not soluble in water. So as the calcium carbonate is undergoing formation, it actually precipitates on the surface and networks all these small slag particles together and encompasses the aggregate sometimes and forms a big network of 3D structures that leads to fortification. The key things about this whole process is that you need a very thin film of water to have the calcium come out. If you didn't have water, if you just take slag particles that are dry and you expose it to CO2, nothing happens. The dissolution of CO2 is also a critical factor for this process to happen because ultimately you need the calcium carbonate to form in the aqueous layer, but actually precipitate out onto the solid surface. The process of reaction of calcium with CO2 is called carbonation. This technology was already developed, at which point they were looking for a chemist to solve a couple of issues that they were having in terms of looking at the optimal conditions by which this process could be made better. By better, what I mean is they found that obviously industry wants to produce more product at a smaller given amount of time. So they were obviously very interested in exposing the precast cement blocks to very high pressures of CO2. And they kept telling me that the CO2 only reacts at the surface. And what happens when you expose the precast blocks to CO2 is essentially you form what is known as saturation kinetics. Again, keep in mind that calcium carbonate is not soluble in water. So when you expose this precast block here, it has a mind of its own, but we'll work with it. Okay, let me see again. Okay, there we go. So what happens is you form tiny crystals of calcium carbonate, which actually form a barrier through which CO2 can no longer pass. The trick was to figure out essentially the optimal partial pressure of CO2, which would allow enough calcium carbonate to form to encompass all the slag and aggregate particles, yet still keep some hollow spaces inside so that more and more CO2 could actually permeate to the inside to network the whole structure. So at that time, I was just playing around with finding out the pH of pore solution. So every day I would get covered, well, secondary effect, but primary is I would take buckets of slag and place them together and pour water in it and then let that sit for a while and with Pasteur pipettes microscopically take out the water between the two particles and check for the pH. Once we've figured out, we did some rudimentary modeling of the pH solution, and we found that there was a very good dependence of the pH dependent on how far deep into the sample you're going. I can't exactly give out the details here because they're protected by patents and NDAs, but nonetheless, the pH of the pore solution is critical in affording good carbonation. The solubility of CO2 is obviously published in literature since the 1960s, so that was a no-brainer there. But we also had to look at diffusion of CO2. Particularly, we looked at diffusion of CO2 as a function of the crust that was forming on the outside of the sample. Once we had those controlled, we were able to reach the right point where the calcium carbonate crystals that were formed inside were not too big and not too small, just right. Because if they're too coarse, they don't connect the different components of the concrete block together. If they're too fine, then they don't also connect to each other. So the right optimum calcite crystal size is critical for the good strength of the concrete. Now, that being said, as academics, engineers, and people of the scientific community, we are sometimes not very adaptive in terms of taking new technology. Not to mention that when you're building houses and bridges, if I came and told you, hey, I have this better material that is better than concrete, your first question to me would be, is my building going to break down? Right? So it takes some time for all these regulations to kick in and all these testings to be done. While at the background, we were basically looking at SEM spectroscopy, and I know I have an SEM spectrometer here. This is what I was talking to you about before. We did a bunch of SEMs to figure out the optimal size of the CO2 crystals, the calcium carbonate crystals that were formed inside, and we're able to map out the exact pressure of CO2 and the pore solution pH that was needed to have the best type of concrete. So overall, the process of making slag into concrete is essentially you go and you talk to the blast furnace guys, so essentially the mining industry and the iron extraction companies, and you tell them if they'll give you the slag for free. And they're usually very, very good with that because that saves them a ton of money in terms of transporting the slag, which they have no use for, onto the dump sites. So my company was able to create a nice friendship with talking to different companies, specifically one of them that is famous in north of Quebec, which is called ArcelorMittal. They have a huge mine in Fairmont for extraction of copper and iron. So the slag that is brought back gets ground in-house. There are some recipes for the slag being ground. If it's too fine, it's bad. If it's too coarse, it's bad. Again, related to what I was telling you about before. Then you obviously don't use cement because cement is carbon positive, strikingly so. You replace the cement by slag, and you take molds and you essentially form your desired shape. If you're building blocks like this, these are called CMUs, which stand for concrete masonry units. You can also make smaller blocks depending on the purpose. You precast them with water, which are not cured yet. Then you take that and you put that into a CO2 chamber. Again, we've we solved the big issue here because previously they were trying with pressures that cannot be used without special permits. If you want to use, say, 4 megapascals of CO2 and you're starting to set up a company, the first question people will ask you is my CO2 tank going to explode? So one good thing that came out of this research was that the CO2 pressures we figure out were optimal are actually just slightly more than the ambient pressure of the atmosphere. So 1.2, 1.3 atmosphere. Then that block after curing is taken out. So normally for any of you who work with cement, I hadn't obviously, the process of cement involves making the precast block and dipping it into water for 24 hours. Only after 24 hours is this even strong enough for you to actually take it out and handle it. So there's obviously a 24-hour at least curing time for cement. We beat that time by 19 hours. It's not a big difference, 24 versus 19, but it still can be done. And then once they're cured in the CO2 chamber, they're perfectly strong to be used in concrete industry. And I believe some of the regulations have just been passed, and actually Carbicrete is now in the production phase where they're actually making carbon negative concrete blocks. And not only is this Canada's only carbon negative construction company, it's also one of the world's only carbon negative construction companies. The process involves, as I mentioned, CO2 uptake, mix ratio, and processing time. But really the properties that, in order for you to beat the concrete industry standards, the properties you're looking for are compressive strength, density and shrinkage, and absorption properties. So for example, you build a house and it starts raining. If your concrete blocks shrink too much or expand too much, your building would collapse. So these are critical things that construction industry looks at. And before moving to Montreal, the only place I spent time within Canada was Vancouver, where obviously freeze-thaw resistance is not that big of an issue, but in Quebec, it is a big thing. So for Quebec regulations to be passed, there was something that is called freeze-thaw resistance, where you essentially take a sample concrete block and you freeze it, you thaw it, you do it over time, and you see how it resists degradation. And thankfully, with the new technology that we filed a patent on earlier this year, it took us about a year to write that patent, but nonetheless, all these three things were addressed, and that basically concludes my talk today. This is just repetition, but this is some pretty pictures from how we were making concrete blocks here. This is one of our engineers who takes these concrete blocks and puts them in chambers to test, to have for further testing. I know this is this slide was forcefully, my company told me to put this slide in, but it's an advertisement essentially that Carbicrete concrete does not use cement. It's made with steel slag, which is otherwise a waste product from industry, and it's cured with CO2, making it carbon negative. So that's it.
Hi, great talk. My name is Collins. So I have a question here that's hitting me in the head. My question is, what you've just delivered, the information regarding that cement is one of the major contributors of CO2. I want to ask, is this a widely known phenomenon, or is just born out of research that is recent? The reason why I'm asking this.
Yeah, so correct me if I'm wrong. Your question is the fact that I said, or the fact that cement is the major contributor of CO2, is that a widely known fact, or is it an outcome of recent research?
Correct.
That's a tricky question to answer. It's not a widely known fact. But when you tell people that it's a fact, the reception is, oh, okay, that makes sense. The reason it's not a widely known fact, and the reason it's more of a buildup on recent trends, is because A, awareness for CO2 is increasing as we go forth, right? The other reason is the cement production has also escalated. As we're chopping down more forests, that's a different story altogether, but we're building buildings for which we need more cement, for which countries like India and China are ramping up cement production 200, 300%. So I don't know the exact numbers, but I would say 30 years ago, cement was probably not the major contributor, but now it is. So I hope that answers your question.
Not so much a question, just a comment. About a decade ago, I had a chance to go down to the University of Arizona. They took over Biosphere 2, which, if you've seen the movie Biodome, is the idea behind it. But they essentially locked 6 scientists into this enclosed capsule thing. But one of the things they didn't take into account was the concrete curing for the ocean biome that they had created. So they basically had to crack the windows because the CO2 concentrations were just through the roof. So,
yeah.
Even when they were designing this huge biosphere, like multi-million-dollar project, like tens of hundreds of millions of dollars, they didn't take into consideration concrete curing either. So, it's certainly an ongoing issue. My question, though, is what's the cost per block for this versus a source block, if you will, rather than a sink block?
I had it somewhere. Did I have it?
Didn't see any dollars.
No. No. It's essentially for concrete industry to accept a new technology, contingent upon obviously it meeting all the requirements. It has to be 4 cents cheaper per CMU block. And CMU block is somewhere between 18 to 21 kilograms. So that one of those is 1 CMU block. That has to be cheaper than 4 cents for even people to consider buying it. Depending on where they're produced, I think in Canada, it's about $4 or $6 US. They still use the US system per CMU block. So that gives you a perspective of how, but Carbicrete, I left in 2022, at which point they still hadn't entered production phase, but now they are in the production phase, which means obviously they could meet that 4 cent difference. And again, this is show off, and this is my company talking. I'm not there anymore, but they've said that by 2035, 50% of blocks, 50% of construction in Canada will be Carbicrete, according to their projection of production. Well, yeah.
I've got a question online. Michael asks, and there's a few pieces to this. Sorry.
Could I go back to the original?
How does slag concrete compare with cement concrete in terms of weight and tensile strength? Are there specific data? Will using slag concrete help reduce the overall dead weight of buildings, which structural engineers work hard to limit, especially when reinforcements are required?
Okay. So this answer is twofold. For the regular CMUs, there's absolutely no difference. In other words, if I gave you a CMU produced from regular concrete and a CMU produced from Carbicrete concrete or slag, there's no difference. If you're a forensic scientist, you could figure out the difference, but the only way you could figure out the difference between slag-based concrete versus regular cement-based concrete is by doing SEM and EDAX on profiles that have been taken from the samples, but they're chemically equivalent. In terms of dead weight, they're also exactly the same. Now, there is a project, not by Carbicrete, but another company in Japan, because Japan is, as Dr. Yasu can attest, riddled by earthquakes. So there is a company in Japan in Kobe, and Kobe produces a lot of steel. So Kobe actually deals with a lot of steel slag. So this company in Kobe is actually not working on these type of CMU blocks, but they're specialized in making lightweight concrete blocks where before carbonation, they actually aerate the sample to make a bit more foamy product, which is lighter in weight, same volume, less mass, and then they carbonate it, and they get lightweight concrete for buildings that are the impact of earthquakes on which would be tremendous, like bridges and high buildings and stuff.
Very nice talk,
Thank you.
Shrin. Seems like you're going to be richer than any other
Oh,
faculty.
I
in this.
waived the financial rights for this.
Okay. I'm just teasing you. Okay, so my question has two parts in it. First is that if you take the carbon out of it, is it affecting its stability? Because you're talking about, how
You mean
earthquake.
after curing?
Yeah, after
You
curing.
cannot take out the carbon dioxide.
Okay,
After curing is permanently locked in.
okay. But if you can make one, like the one you were suggesting, is that gonna be more stable than
Make one, sorry, how?
like more stable by structure, like because you are taking out, in my head it's carbon giving it more stability, you are taking CO2 out of it. Hypothetically, is it affecting somehow the stability of the structure? Like the cement is something we think about, as you say, it is a building structure, right?
Right,
So
so
I'm
building 3D networks, obviously, if you deprive it of CO2 in the beginning,
yeah.
or you take out CO2 in the end,
Mm-hmm.
it will lead to disadvantages in terms of structural strength. Absolutely, exponentially to be exact.
Okay. The other part is that does it affect anyway the insulation or heat production?
No, it does not. So that is not a requirement based on construction industry, because those are the three parameters I've shown before are the only criteria that the construction industry cares about. So on the right-hand side, the only thing that you need to do in order for concrete industry to accept your product is compressive strength, density, shrinkage, and absorption, and freeze-thaw resistance. These are the three pillars of concrete industry. That being said, we all know, like even yesterday, I got a pamphlet from Hydro Manitoba saying insulate your homes and we'll give you a rebate. So as those things are catching up, I imagine in a couple of years, people will also start emphasizing how good your concrete is in terms of insulation. But as of now, we've never tested it. We don't know. And I don't have any data to give you.
Okay, thank
But
you.
if you ask me my feeling, I would say these, because of the higher percentage of iron in these, I would imagine these would be better conductors than regular concrete.
I was just wondering about the concrete producing reaction. You said there is carbon dioxide release during C2S and C3S
I mean,
production.
cement production.
Cement, yeah. And from cement, the concrete is producing later on. And there is another carbon dioxide release with time.
Secondary strength.
Yeah. So if these two reactions, the second reaction is like occurring later, not in the same time, then how the first carbon dioxide is being neutralized by the second carbon dioxide?
Fantastic question. If they were in the same molar ratios, they could cancel each other out, but that's not the case. The amount of CO2 generated in the process of making cement is 10 to 15 times higher than the amount of CO2 consumed by the concrete product years after it was sent.
Okay.
So typically the CO2 used leads to a decrease in the pH of the concrete block. That time scale is of the order of decades. So when you see your old buildings crumble, one of the main reasons is that the pH has fallen because that concrete has undergone reaction with atmospheric CO2 over time. And that leads to de-strengthening of that concrete. But that time scale is the order of decades, whereas this one is 15 times higher in a time scale of overnight.
Well, that's how it stays in the atmosphere then. Okay, thank you.
That was a nice presentation. You did so well. I would have asked you some of the chemistry aspects of the presentation, but for time's sake, I will ask you, just as Collins asked you, it is a kind of a new innovation, and I'm going to ask you, what role do you think that policymakers and governments can play to promote the use of this new innovation? And my second question would be, I want you to kind of throw more light on the calcination process. Because if I should liken it to biology, we know that C6H12O26 plus 6O2, okay, under reversible reaction, we produce 6CO2 plus 6H2O. Okay, now for the calcination where you use the silicon oxide and the calcium trioxide carbonate 4, I want to ask you to throw more light on the calcination process. My first question is, how can policymakers and government promote the bicarbonate? And then second one would be the calcination process.
Okay.
Thank you.
Very detailed question. I would suggest we meet sometime later to discuss this. Okay. But that being said, I'll give you my few cents on this. First, about your question about how governments and policymakers can, promote this innovation. So they already have, because this company has moved on to production stage. But I have no clue about how, to be honest, I joined a company to understand just that, and how shareholders and meetings happened and how financial dealings happened.
Okay.
All I know is that some important looking people sometimes came to our company and we had free pizza. What happens in the backdrop is something as researchers and engineers and scientists at a company. And keep in mind that when I say the company, that was evolving from a startup phase to a production phase. So I saw it evolve. Usually you will never know about it. So the people, for example, at Pfizer who developed the mRNA vaccine have no clue about the financial aspects. That being said, if I had to answer your question, if I were a policymaker, in fact, one of the persons on the patent is now working at NRC in Ottawa. She hates it there, but that's a different story. She told me that the key aspect of policy and for governments to adopt a new technology is awareness.
Yep.
And that's exactly why PR and all these things are important, because you generate enough traction that gets people interested. So that's I know I'm not really giving a good answer to that, but that's all I know,
That's fine.
unfortunately.
That's fine.
And as for your second question, come see me sometime else, but we need
Okay.
to actually write
Yeah,
down the
yeah,
equations
sure,
and we can
sure.
do that.
And I've got one from online, and it's actually fairly connected, but a little more to it. So Christabella Dusser asks, since there's not been a lot of awareness to the public about this alternative for cement, what measures are being put in place to spread the news, especially to African countries? So I don't know if that's something you can speak to.
Not really. I wish I could, but based on, again, my exposure in this company, the main, I don't want to use this word, but I won't use it. Never mind. The main developing countries that are in partnership with Carbicrete are India and Sri Lanka and Uzbekistan. I don't have any data about African countries. But again, correct me if I'm wrong, I don't know the geology. There's always a geological backdrop to all these answers. The reason, if you look at India, Uzbekistan, and Sri Lanka being players in contributing to this economy, is that these are all countries who have a lot of limestone. Therefore, if you have a lot of limestone, and I can correct me, but if you have a lot of limestone, chances are you have a lot of metal refining sites, because that's what's used to refine metals. And therefore you generate a lot of slag. In fact, I don't know how much you guys know about one of the biggest corporations in India is called Tata Corp, and they essentially own India. And one of the biggest products that Tata makes is iron and steel. So in fact, one of the biggest investors for Carbicrete is Tata Steel. And the reason I know about Kobe is because we originally wanted Kobe Steel to come in and partner with us, but that didn't happen because they were already partnering with the other company in Japan. So yeah, so to answer your question online, any country that has big limestones will typically be a big partner or player in this field.
Yeah, great presentation.
Thanks.
I'm just wondering, like, for this innovation, you're strictly using carbonates as the binding agent. Is it?
Theoretically, yes. So let me rephrase it. We're using the steel slag as a binder, which has calcium oxide.
So it's,
which in water forms calcium hydroxide, which undergoes CO2 to form calcium carbonate.
okay.
So the end product of the binder after carbonation is calcium carbonate.
Okay. And then for traditional one, it looked like you're forming silicates, correct?
Correct.
Yeah.
Silicate hydrates.
Yeah. So how does that compare for strength and durability? If you're using?
That's what we had to match. That's
So you
what
matched it.
We overshot actually.
Really? Okay, that's interesting.
Yeah. And as much as it will sound a show off, one of my patents actually also, one of the things I discovered in the patent was solving the freeze-thaw resistance. It led to an improvement of 400% as opposed to regular concrete for freeze-thaw resistance. I can't tell you the details. I'd have to kill you otherwise.
Thank you.
Hi, it's me again. I just want to add to this, a contribution now, not a question, to the question he asked with regards to policymakers and the countries and everything. So I quickly Googled the map of iron producing countries, and Africa is in the dark.
Is in the dark?
Is in the dark.
So
with regards to policymakers, unless the majority of the African countries that don't produce iron would want to start importing slag, which of course will increase the cost of buildings.
That is actually the rate, the biggest offset. Slag is heavy. To transport it via ships and containers is a big deal. Now, I know the facts here. Tata Steel would not have partnered with Carbicrete because India to Canada is a long way. And I know, believe me, I know. It takes 18 hours for me to go home every 3 years. But just to ship that, they wouldn't have shipped their slag unless they had other shipments coming for other things. So it you know, to kind of relates to your question also, it's not about a single policy taking into effect something. People will always try to maximize gains, right? So if you have other infrastructure running and you can couple it to something else, you might get lucky.
So it's actually another question from Michael, a follow-up. And again, it's got multiple parts. In chemical terms, as you obviously indicated, the molar quantity of CO2 produced from cement production in the kilns is about the same amount of CO2 removed by concrete mix from the atmosphere after the chemical reaction is complete, perhaps in a couple of months. My question is, why don't researchers talk about the fact that net positive CO2 emission from cement production is from the manufacturing process, i.e. energy input, and not from the chemical process, which is about the only thing ever talked about? Would your technology survive the competition if the process of cement manufacture became energy efficient and cost effective?
Fantastic. Probably the creme de la creme of the questions. I'm sorry, I can't rephrase the whole question, but I'm trying to work out the answer here. In a sense, you can never make the cement production process produce less CO2. Unfortunately, that's a fact. It's governed by the chemical equation. You cannot change the amount of CO2 generated per amount of calcination or moles of calcination. That's something you just can't do. So no, I don't see a threat to alternative concrete industry, especially when comparing to cement-based concrete industry.
So I guess in the kind of grand scheme of things, your goal is to lower carbon emissions, correct? In a way. So I'm just looking upstream here. How do these mining and blast furnace processes like compare? Like, are they clean practices, and do they release a lot of carbon as well?
They do. They do. But look at it this way. It's evil, but it's a necessary evil. I understand that this technology is reliant upon a dirty industry, quote unquote, of blast furnace and mining metals, right? But that is something we need. So yes, I know it's a little bit of a trickery, But you don't count that because that's already accounted for a different process. You start here, assume that you're at 0 and see what your net change is from there on.
Makes sense. Thank you.